In this video, we're going to look at the principle of line differential protection, one of the most reliable and fastest protection methods used in modern power systems. We'll start with the basic concept, then walk through how the protection behaves during normal operation, external faults, and internal faults. Finally, we'll touch on practical aspects such as charging currents and the differential characteristic. Line differential protection is based on a very simple and powerful idea. What goes into a protected line must come out. The protected zone is clearly defined by the locations of the current transformers, or CTs, installed at the ends of the line. This is what gives differential protection its high selectivity. Each relay measures the phase currents flowing toward the protected object, such as a transmission line or cable. These currents are converted into fundamental frequency phasors using Fourier filtering. The relay then compares the local current with the current measured at the remote end or ends of the line. If the currents are equal, the system is healthy. If there is a significant difference, it indicates a fault inside the protected zone. Because the comparison is done directly between line ends, no intentional time delay is required, making line differential protection essentially instantaneous. However, this principle does require a reliable communication link between the line terminals. Line differential protection offers several important advantages. First, it does not require voltage transformers. Only CTs are needed. Second, it provides 100% line coverage without time grading. It is suitable for both short cables and overhead lines, as well as multi-ended or tapped lines. It also works well in more complex applications, such as lines with series compensation, or lines that include transformers within the protected zone. Another major advantage is its immunity to external system conditions. Parallel lines, power swings, and different grounding methods do not affect its operation. It is also very sensitive to high resistance and arcing faults, while requiring relatively simple relay settings. On the other hand, there are some limitations. A communication channel is mandatory, and it must be supervised to ensure reliability. Differential protection only protects the defined zone between CTs, meaning it does not provide backup protection for external equipment, such as adjacent lines or transformers. Normal load condition. Under normal load conditions, the current entering the line at one end is essentially the same as the current leaving at the other end. Small differences may still exist due to CT measurement errors, such as slight phase shifts or amplitude inaccuracies. These errors produce a small differential current, but it remains well below the operating threshold, so the relay remains stable. During an external fault, large currents flow through the protected line, but the fault itself is outside the differential zone. Ideally, the currents measured at both ends are still equal. However, CT errors become more significant at high current levels, and CT saturation may occur at one end before the other. This can result in an apparent differential. In the case of an internal fault, the situation changes completely. The current entering the protected zone is no longer equal to the current leaving it. As a result, a high differential current is detected. This condition clearly indicates a fault inside the protected zone, and the relay must operate immediately and issue a trip command to isolate the faulted line. For long cables and overhead lines, capacitive charging current becomes significant. This charging current appears as a differential current, even under normal operating conditions. Without compensation, it could lead to false operation. Therefore, the protection system must account for this effect, typically through additional stabilization or compensation methods. To ensure both sensitivity and stability, line differential protection typically uses a dual slope characteristic. The first slope, often called M1, covers normal measuring errors. The second slope, M2, accounts for more severe conditions, such as signal distortion or mild CT saturation. A changeover setting defines when the characteristic transitions from the first slope to the second. The exact values and scaling factors depend on the relay manufacturer, but the principle remains the same. Remain stable for external faults and operate reliably for internal faults. To summarize, line differential protection is a fast, selective, and highly reliable protection method. By directly comparing currents at the boundaries of the protected zone, it provides instantaneous fault clearance